Welcome back to Differential Equations. In this video, I want to talk about linear independence. The idea of linear independence is one of the fundamental ideas in the study of mathematics in linear algebra. And so if you've already taken a course in linear algebra, this should be very familiar to you, and quite honestly, there shouldn't be anything new in this video. But if you haven't taken linear algebra in the past, I want to quickly summarize some of the most important ideas from that discipline. If you're interested in looking at any of this in more depth, the study of linear algebra is open to you. Specifically in linear algebra, we talk about linear independence in terms of vectors. And one of the really interesting things in linear algebra is showing that things that don't feel like vectors at all can actually be thought of as vectors. Specifically, in this video, we're going to be looking at functions and pretending that functions are vectors. And the traditional study in linear algebra doesn't really handle functions as vectors all that nicely. So I also have to mention that the branch of mathematics called functional analysis looks at that particular aspect a little bit more carefully. So a couple of places you might want to go if you want to continue studying these ideas. Let me get my head out of the way though, and let's take a look at some more practical ideas of what I'm trying to talk about. We established previously the idea of a linear combination of two functions. Some constant, I'm going to use a times f of x plus some other constant b times g of x. And we used different letters previously, but I think that since we're talking about functions in the abstract, getting to the comfort and familiarity of f of x and g of x is probably going to make it a little bit easier to work with this. The idea of linear independence is observing that if we pick that a is equal to b is equal to 0, so both constants a and b as 0, then we get the null function. F of x is equal to 0. Put anything into the function, it spits out 0. It is the most boring function imaginable. And if we pick a and b equal to 0, then we get this. Our question is, can we find another pair of numbers, another pair of a and b, so that when we take the linear combination, we get out 0? If we can, then the functions are linearly dependent. If we cannot, then the functions are linearly independent. So those are our watchwords: linear dependent, linearly independent. And there are some powerful tools that we can use in order to do this analysis. If you have studied linear algebra, you may have seen some of them. I want to point out that there are a couple of them even mentioned in our textbook. The Wronskian, our textbook talks about, is related to this. I don't want to get into that. It's a lot of technical detail. It doesn't really help all that much. Instead, I want to look at this in a much more practical sense. So let's just jump in with an example. F of x is equal to x, g of x is equal to 2x. And we want to see if these two functions are linearly independent or not. Well, the general rule is we have sum a times f of x plus sum b times g of x is equal to 0. And that's more complicated than I would like. So I'm going to rearrange this equation by dividing both sides of the equation by a. Right, so I'm introducing a new constant, I'll call it c, and it's just b divided by a. I don't care about the case when a is equal to 0, because if a is equal to 0, then I'm heading down that path of the trivial solution that we already established exists. So I can confidently say that a is non-zero, and by establishing this new constant c, I've taken our equation from an equation with two unknown constants to an equation with just one unknown constant. And that's going to be the tool we use. Rearranging c is equal to the negative of f of x divided by g of x. Now plugging in, we know that f of x is x and that g of x is 2x. The x's cancel each other out, leaving us with negative 1/2. All right, so the ratio b over a is equal to negative 1/2. Any values we can find for a and b that satisfy that will give us the result that we're looking for. A times f of x plus b times g of x is equal to 0. That's actually more complicated than we need. I don't care what specific values there are, I just care that they do exist. I said that c was a constant. I plugged in the functions, I did some algebra, and I arrived at a constant. And because I was able to do that, that's enough for me to claim that these functions are linearly dependent. If we plug in the functions and we actually get a constant, then the functions are linearly dependent. If we plug in the functions and we get something that is not constant, then the functions are linearly independent. Although that has its problems, right? When we originally plugged in, we got x over 2x. It's not immediately obvious that that is constant because there are x's involved. And that's why the more powerful techniques like the Wronskian exist, because we can use this to clearly say when functions are linearly dependent. It's a little bit harder to use this to say when functions are linearly independent. But that's okay, we can manage close enough for our purposes. As another example, let's take a look at f of x is equal to x and g of x is equal to x squared. Well, we saw before that we're going to be looking at a constant c, which is the negative of writing this backwards, sorry, f of x over g of x. And if we plug in, this is the negative of x over x squared, which is the negative of 1 over x. That is a very simple function. There's no cleaning up left to do. This is not constant. And because this is not constant, we can conclude that f and g are linearly independent in this case. Let me take a look at one more set of functions. Sine of x and cosine of x. Sine divided by cosine is tangent. Tangent is not constant. That's something that we are going to take extensive advantage of in this course. Very specifically, sine and cosine being linearly independent is going to be something that is used in about a third of the differential equations that we study for the rest of the course. All right, I would like you to take a look at this last set. F of x is e to the x, g of x is e to the 2x. And I want you to determine, are these two functions linearly independent or linearly dependent? Take a couple of minutes, see what you can do with that, and I'll see you in the next video.